Okay, no problem. Okay, so let's continue. So this is the second session for today. It's a little bit longer than the one before, so let's see up to which time are you willing to stay. And it is related to one of the applications I wanted to discuss in my visit this time to Perm, which is integrated microwave photonics. So the session was divided in two parts, more or less is 1 hour each, I think. So the first one is microwave photonics, from discrete components to application-specific photonic integrated circuits, and the second part is integrated microwave photonics processors. Okay, so let's go to the first one, to the first part. And this is divided in what is microwave photonics, a description and applications, the architectures, ingredients and functionalities of a microwave photonics system, the motivation for integrated microwave photonics and application scenarios, and then the state of the art of the and degree integration in this field. Okay, so what is microwave photonics, description and application? So microwave photonics is the manipulation of RF signals using photonic techniques and components. On the one hand, you have microwaves. Microwaves usually use heavy cables with high loss at different frequencies, which are rigid and have a large cross-section. On the other hand, the optical fibers are lightweight, are low loss, and are somehow flexible, or comparatively more flexible. Okay, so this microwave photonics is the one that brings high frequency in the RF domain into fibers to process the signals. Okay, and we can divide the activities in microwave photonics in these main 4 fields. You can find many descriptions. This is one of them by Dr. David Marpang, which is a very well-known researcher in this field. And these are signal transport, signal processing, signal generation, and signal measurement. Signal transport deals with with moving one RF signal from one side to other, as the name indicates. And in this case, we are talking about microwave photonic links. Now I'm going to describe a little bit which are the parts that you require to move one RF signal from one location to another using photonics. Basically, you need 3 things: a conversion from the electrical to the optical domain, a transmission media, in this case the optical fiber, but it doesn't need to be optical fiber, but an optical fiber, optical transmission media, and then at the other end, the optoelectronic conversion to get back the RF signal. Okay? This electro-optic conversion can be done by many different means. For instance, via an intensity modulator, phase modulation, single sideband modulation, or even a complex modulation. Okay? In any case, there are different challenges in these microwave photonic links, which are, first of all, conversion losses. Okay? When you translate your RF signal to the optical domain, or when you do the other way around, back from optics to RF, there are losses. Okay? So that means that end to end you are going to have a gain, which is typically negative. That means that you have losses. Okay? Then you typically will use an optical source, which is a laser that has a phase and intensity noise, which actually is something that you don't have in the optical domain, but because you are using the photonic domain, you're going to have to take it into account. Next, in all these conversion processes, there are non-linearities, not only in the conversion from electric to optic and optic to electric, but also with the non-linear propagation in the fiber, as well combined with the dispersion. They give rise to non-linear distortion. We'll see it in the next slide. And of course, since you're using a photodetector, you are adding a photodetector shot and thermal noise. Okay? So, for instance, in this slide, it's still signal transport microwave photonics links. This is incorrect. And you have your RF in. A typical test signal or test method that you use is a 2-tone probe. Okay, so basically you put 2 frequencies into your optical system, RF photonic system, and then you look at the output. You still get the 2, but you get all the beatings because of the non-linearities in all the system. And you get also an increased noise figure. You can see here, this is minus 80, this is minus 80 as well, this is 0, 0, so actually same vertical scale. You can see the noise has grown because of the thermal and photodetector noise as well. And that you have intermodulation products. These are harmonics at the sum or 2 times the frequency, and this is the difference frequency. But actually the most important are these ones, the intermodulation ones, because they actually fall in the band of interest. Okay, we are making here an example with a 2-tone probe system, but actually in practice these signals are modulated, so they have a bandwidth. Okay, so there is signal content all around here. If the intermodulation products fall into the signal content, these are interferences. Okay, so there are ways or different figures of merit to characterize your microwave photonic link system, which is the link gain, which is the relation between the RF power at the input and at the output. Typical is minus 30 dB. So actually you end up losing, without an RF amplifier, you end up losing power. Okay? Good would be not having any loss. Okay? It can be done as well with other techniques. Noise figure, which is SNR in, SNR out. This SNR in divided SNR out, or subtracted if you are operating in the typical 30 dB. You have more SNR typically at the input. Good if it is less than 10 dB. And then dynamic range, which is the margin of noise and distortion, basically, which is the difference between this amplitude and this amplitude. Typically 80, 90 dB, good 110 dB. Okay? Any question? That was the first part, microwave photonic links. Okay? First part of what is microwave photonics. Second part is signal processing with filters. Basically, the scheme is the same. You convert your RF signal to the optical domain and later back to the electronic domain from optics. But in the middle, instead of transporting, you are putting a photonic device which does filtering. Okay? And this has application, for instance, in what is called spectrally crowded environments, where you have many frequencies around and you only want to get one. Okay, that is not a problem that the regular microwaves cannot solve. That is a problem that the regular microwaves can solve. But then consider that you want to do it tunable in a broad range of frequencies. That is something difficult with the regular microwave techniques. And that is the case of wireless communication, the forthcoming 5G communications, and also in radar and early warning systems. So basically, what you want to do is to filter out frequencies and just stay with your signal. And for that, you need a very, very, very high quality filter, which is actually something that can be done in photonics. But as I said, you need to be able to use it in a frequency agile manner. That means tuning it to one or other frequency. So that is something that photonics can do for you. Then there is another type of filter, which is, well, we will discuss about this quite more in the coming slides, which is a delay network. And we were discussing before when there was a question about the beamforming related to the Blue Space project before and beamforming. For instance, the application is on satellite communication, but rather than to Earth stations, to moving targets like an airplane. Okay, if you want to have, for instance, a satellite television on an airplane, okay, how can you do that? Okay, so you can have an antenna on the airplane and you can beam steer it to the satellite. Of course, the plane is moving and you need to keep moving your beam pointing to the satellite. All of us will acknowledge that having a mechanical antenna on the roof of the airplane is maybe not a good idea, because it has like a drag, so actually it has aerodynamics which are not the ones of the plane, and it also, even if you engineer it, there is drag and there is a fuel consumption. Okay, so actually you would be very happy with a patch antenna, okay, with a patch antenna of elements, and then you need to fit the antenna elements with the different signals, so when they are combined, the beam is steering in the right direction. Okay, this can be done with a technique which is called tunable through time delay. Okay? Because if it was not required to be tunable, maybe photonics is not of use. I mean, if it is an earth station all the time pointing in that direction, well, that is easily done with regular microwave techniques. But if it is tunable, it is better done with photonics. Basically, here you can see a tap and delay network where you have 4 antenna elements, the beams coming in, the beam coming in, and then it is sampled by the different antennas, and because of the delay, you can point in one or other direction. Okay? So basically, what microwave photonics pretends is to substitute the way of doing regular microwaves, which is actually having your sources, your microwave components that somehow take these signals and do something, and your detector sources or again antennas. And then this is a traditional RF system operation, and then what microwave photonics propose is to take these signals down to the optical domain with a modulation scheme. We later will give some more details on the modulation scheme. Have an optical core, so now you have this in baseband, this is your RF frequency. In the optical domain you have this on the optical carrier and the 2 side bands. Then you put it to the optical core, which is some photonic element that does something. And then you end up with a signal processed in the photonic domain. And when you come back, it is equivalent to what you had in the microwave environment, but with additional features. Okay? Because, as I said, the most important thing is that photonics can be comparatively easier reconfigured than the microwaves. Okay? So basically you can do very fancy things with the microwave photonics. Okay? Okay, so if you wonder yourself which are the applications and functionalities, well, first of all, in the macroscopic world, all signals are analog, and basically what we do to have them again in our devices here is to acquire them and to digitize them, to pre-process them and digitize them for us to see them in our digital computers. Okay, so this signal acquisition and transport can be done electronically, but for instance, for some frequencies which are really, really high, and in environments where you need reconfiguration, electronic acquisition is not the best thing. Optical sensing, transport, and acquisition is the best thing. Of course, there is analog processing, analog to digital conversion, and hardware to digitize these signals, but there are alternatives as well to do analog optical processing. We will see some examples at the very end of this session, on session 2B, the second part. And then there is also the possibility of make analog to digital conversion photonically, and of course to do some pre-processing of digital signals optically. And about functionalities, you can have, as I have mentioned, tunable and reconfigurable filters, optoelectronic oscillators, which actually are devices which are a mix of optics and electronics and can provide very, very pure tones for later RF transmission or processing. Arbitrary waveform generation, which is actually something interesting in the sense that you can have like a spectrum to fill, and you can have like a template with frequencies allowed and not allowed, and you can fill them by engineering the time domain, and that I'll show something later on. And a lot of them, frequency mixing, digital analog conversion, true time delay, I'll stop on this, and tunable phase shifters later on, instantaneous frequency measurement, I'll give an example in the second part of the talk, and many others. Okay? Any question up to this point? Am I going fast or? Okay.
Смотрите, что у нас получается ситуация, когда мы хотим работать в диапазоне 6 частот, нам необходимо каким-то образом каким-то образом совершить передачу свечей сигнала в оптику, из оптики обратно в то есть и получается, что у нас несколько шагов по конвертированию электрического сигнала в оптический, из оптического в электрический обратно. В связи с этим у нас возникает большое то есть большое количество документов на этапе приема этого сигнала и обработки этого сигнала, управления. Кроме того, здесь решается проблема по, если мы хотим создавать антенны, чаще всего антенны наши понимания, что вращающиеся, то можно с помощью технологии интегральной схемы создавать перестройку передачи сигнала, не вращая без вращающихся элементов, просто подавая различные сигналы на элементы, устраивая фазу оптического луча, далее управляя волновым фронтом. Что еще здесь у нас получается? Maybe go. Yeah. Кроме того, для того, чтобы обеспечить весь функционал схемы в свечах диапазонах, нам необходимы все-таки отдельные элементы, которые сами по себе разрабатываются, имеют какой-то ограниченный функционал, но для того, чтобы это все, для того, чтобы вся система функционировала в диапазоне свеча, это все должно работать, должно быть интегрировано на схеме или каким-то образом присутствовать. Или этот функционал должен быть реализован. Чаще всего мы ведем на слайде, да. Чаще всего для того, чтобы это все осуществить, типический сигнал подается на модулятор. На модуляторе уже оптический сигнал с помощью электрического поля моделируется, электрическим сигналом на заданных частотах передается в схему, в рабочую, функционирующую, и далее уже на фотоники, то есть обратно конвертирует. В принципе, вот. Если чем применение, здесь в данном случае связано в основном для применения антенн, передачи сигналов, приема сигналов. Вопросы?
Frequency mixing. Yes, when you have two frequencies and you beat them, you have a higher or lower frequency. Or do you want to know about
Yeah, we are working right now with, we trying to develop signal analysis system for signal analysis.
Yes.
Where we have two different frequencies, we need to beat it also and analyze the general result of this beating. That's why
okay.
the new
I understand, but you have these two RF signals. Your are electrical signals.
RF optical signals.
They are optical signals.
There are optical.
So two lasers, and you're trying to beat them.
Something like that.
Okay, yeah, that is frequency mixing.
I will explain it in details during this lecture.
Not really.
Not really. We can discuss it later, for example.
Maybe. I think I have materials in Valencia I can give you, because I have a colleague working actually on terahertz, so maybe it's better, different techniques that they use. Okay, good. So now next part is architectures, ingredients and functionalities for a microwave photonics. Now we have described in general what it is and the applications. And now let's discuss what you need to make it work, okay? So this slide is like an artist's representation of a microwave photonic system, but some years ago we realized that every or nearly all microwave photonic systems of this list I have shown here, all of these can be done with this architecture. Okay, which is something from the engineering point of view interesting, because with a single architecture you are able to generate different functionalities. Okay, so basically the architecture consists of an optical source, a source shaping system, which basically can be a filter, optical filter, electro-optic modulator, different types, and then an optical coupler to maybe divert part of the signal out, another optical filter, optical coupler to couple some light in, and then a detector that can be differential or not, a detector, and then also some parts in the RF domain, amplifier, filter, RF filter, and RF switch, coupler or switch, okay? So, when it comes to the optical sources, you can use many things, okay? You can use broadband sources, you can use narrow line sources, or less narrower or broader sources, or even multi-mode sources, or not only fabricated lasers, but also node-lock lasers or combed lasers, okay? That depends on the different applications. But this, I am just trying to discuss which, or just to briefly show which are the shapes that this optical source, which are set generic, can take. It can take many shapes. It depends on the application. Okay, so just stay with me. Optical source can be one of these. Okay. Then modulation. Modulation can be one of all of these, even with direct modulation of the laser. That means not using this and directly modulating the laser, or electroabsorption modulator that you know absorbs power depending on the signal that you are driving it, or phase modulator, actually changing only the phase of the signal. For instance, what you do in the lithium niobate, you have the arms, the phase modulation. Okay, or if you embed the phase modulator in a Mach-Zehnder, the Mach-Zehnder modulator, and if you nest Mach-Zehnders, you can do even more complex modulators. You can also have ring modulators as well. Okay, a ring resonator that you modulate the ring, and then the resonance shifts this, and your signal is here, so actually it's modulated. Okay, so a modulator, an optical modulator.
If we would like to go to RF communications, we need to transfer signal and receive signal. We need to change it somehow. We need to modulate it. That's why we consider modulation, types of modulation.
Yes, we consider types of modulation because depending on the final functionality of that list that I show, it is best to use phase modulation or intensity modulation, for instance. Okay? Okay. So that's why we are considering modulation.
Чтобы вы понимали, если мы хотим передавать сигнал, принимать сигнал, нам нужно каким-то образом это для этого сейчас наблюдается связываться потихонечку, чтобы не отдельными слайдами ставим, чтобы у нас складывается свою систему.
Okay? Yes,
what about frequency?
Frequency modulation is actually as well a phase modulation thing, because it's the derivative in time. So, okay. Any other question? Okay. Good. We'll see an example in which it is frequency modulation through phase, what you are detecting later on. Okay. So, modulation, and then of course you need detection, the last stage. You may see that I have skipped these two big blocks because I will talk about them later on the other slides of the talk, the reconfigurable optical systems. This I will talk separately, but the basic ingredients, optical source, modulator and detector, that you can use many times, either APDs or PINs. PINs are mostly preferred because they have wider bandwidth, less noise, and they are also distributed designs with even larger bandwidth, which are the traveling waves. Okay. So now this part here. Basically, our research specialized mostly on this part here. Okay, we used all the other ones as ingredients provided by the foundries, but what our core expertise is in developing this element, which is actually key. It's the central element that gives you one functionality or other combined with all the others. So, for this element, you can have either reconfigurable or a new type one that we are exploring recently, which is programmable. Okay, these are basically optical filters. Okay, in summary, they are optical filters, and the optical filters can have many different architectures. Okay, For instance, one is called coupled resonator optical waveguides. So this one here, light comes in at this port. This is an optical coupler. Part goes into the ring, other part goes out, and it goes through the ring, resonates, and then it will go out. Okay. So for some wavelengths, you will have a constructive interference here and destructive interference here, and vice versa. So it's actually all of these are periodic filters. Okay. So this probe here, this probe, if I'm allowed to write the blackboard, this probe here, if you look at the wavelength domain, you will have reflection and transmission. Okay. Reflection is something like this. Okay. And transmission is on the opposite. Okay. So these are complementary. Okay. This is wavelength. Okay. So the more rings you put, the more fancy responses you can make. Okay. More square responses. Okay. More filters. This is like unit cells of a filter. Higher number of unit cells, higher order filter, so better filter. Okay. And this, in this case, this is an infinite response filter because you can see if you pump an impulse here, ideally without any loss, it would be resonating forever. And on the other hand, you have these cascaded Mach-Zehnder interferometer filters, which actually are finite impulse. You put one impulse here, and at the very end you will get a number of impulses there, and everything will die out afterwards. So these cascaded Mach-Zehnders as well are couplers, and I didn't mention, sorry for that, these blue things are phase shifters. Okay, not phase modulators, not modulators to modulate actual signals, but to tune. Okay, to tune, slow tuning. Okay, and they can be carrier injection modulator, thermal modulators, whatever. Okay. And then electro-optic as well, if you wish. And then there is a combination of these two, which is ring-assisted Mach-Zehnder interferometer, which we have studied quite a lot. It consists on a Mach-Zehnder. You can see the Mach-Zehnder. This is the output coupler. This is the input coupler. Okay. But then in the arms, instead of having a straight waveguide from this point to this point, and from this point to this point, you load the arm with rings. Okay. You load the arm with rings, okay? And the nice thing of this filter, if you are a little bit familiar with filter design and filter theory, this filter design and filter theory describes the filters, in particular digital filters, in terms of poles and zeros. Are you familiar with that a little bit?
Probably let's do general introduction.
Okay. There's no need to do that. What I'm going to tell you is the position of these poles and zeros determines the response of the optical field, of the filter. Okay? I'm not talking about optical filters right now. This and this architecture have constrained positions. So you cannot get every filter that you want. You can only get certain types of filters. And this one has unconstrained positions, so you can nearly do every filter that you wish. Every filter shape, not only the amplitude but also the phase response. Okay. You are noticing maybe squares and not squares here, trapezoids, because actually this is a 3 dB coupler. Okay? And these are custom couplers. So the coupling constant in these rings needs to be engineered at a given value for a given filter response. Okay? Okay. So what you're seeing here is a probe, a Mach-Zehnder, a cascade Mach-Zehnder, and a Ramsey. Okay? So once you draw it, it is exactly that architecture. It is reconfigurable, okay? Because you have these tuners, for instance, to tune there. You have these tuners there, here, so you can just move resonances a little bit. But you cannot change this architecture into this, or this architecture into this. Okay, and that is what we call, if you can do that, that is what we call programmable. So this is the one on the left-hand side. Programmable means that you have a physical topology that you can reconfigure and make it look as this one, or as this one, or as this one. So I don't know if you can realize this is like an hexagonal mesh. You can see the hexagon here. Okay? Each one of these is a maxillary technology. Okay? Later on I'll show you a picture, okay? But keep it in mind. By reconfiguring the individual maxillars, you can make with this, you can make this, and many other things. Okay? Okay? I think that you already can see, for instance, a single ring. Okay? A single ring would be entering here, going there, and going. Okay? Okay.
У нас есть, нам необходимо генерировать сигнал, моделировать его, передавать каким-то образом, потом принимать. Для того, чтобы моделировать сигнал, может быть, при лазере и манипуляции, для того, чтобы принимать, использовать детекторы, они были рассмотрены в предыдущем слайде, физическими типами приема и алгоритмами, принципами работы. И теперь мы рассматриваем фильтры. Фильтры нам необходимы для того, чтобы перестраивать нашу систему. You need to tune system?
Yes.
Yeah. Okay. Мы должны каким-то образом перестраивать, настраивать эту систему. И здесь используются различные типы фильтров. На основе кольцевых резонаторов. У нас есть фильтры на основе кольцевых резонаторов, которые, вот, как Паскаль нарисовал, вырезают заданные длины волн, либо наоборот пропускают заданные длины волн. Либо мы можем сделать какие-то фильтры на основе интерферометров Маха-Зондера.
А несколько колец используются для лучшей фильтрации, да?
Несколько колец используются для лучшей фильтрации, они используются для того, чтобы сделать спектр более квадратным. И в данном случае, примерно, эта же схема может быть реализована, ну, в смысле, фильтр может быть реализован на основе интеграции кольцевых резонаторов с интерферометром Маха-Зондера. As I remember correctly, if we will integrate Maha-Zondera interferometer with the resonance of the spectrum, it will be also square or something like that.
You can adjust it and design it to make it look square. Later on, one of the cheap examples I have is this.
Okay, what is the advantages of square?
Well, you usually, yeah, that's a good question.
Probably I will finish with explaining with this picture and then we can continue. И они, получается, разработали эту схему, когда схему с элементами, схему на основе шестигранника, на каждой грани, которая находится в МЗМ, перестраиваем. И путем постройки каждого МЗМ мы можем реализовать одну из тех схем фильтрации, которые нам надо. Потому как, если мы отдельно интегрируем вот эту схему или эту схему, мы не можем перестроить и сделать что-то универсальное. Эту схему мы можем сделать более универсальной.
Okay, the question is, why do we need a better filter response? Well, in telecom and RF, you have your carrier and your subcarrier and your modulated signals, okay? This drawing, you've seen it sometime over there. If you want to filter or to process without distortion, this should be flat and have a linear phase. If you don't do it flat and have non-linear phase, you distort the RF signals. Okay? So that is why you want always to make it as flat as possible to not discompensate the amplitudes of the different bands and the phase, because if you don't have a linear phase, there are relative delays between the different parts of the spectrum which actually distort everything. Okay, so So this table here, so please let's get again into the talk. This part of the talk is I'm just trying to tell every single functionality can be done with this architecture. And that depends on what you select for the optical source, for the modulator and the detector and the shaping system, okay? I've shown you different types of the different elements, okay? And now in this table, what you have is a summary of what you need in each component. Remember, the components were labeled: optical source, source shaping, modulator, coupler output, optical filter that we were discussing in the previous slide, optical coupler output, detector, and the RFs, okay? The RF components: amplifier, electrical filter, and coupler or switch, okay? So for instance, if you want to do an RF filter, what do you require as an optical source? Well, it can be many: laser, tunable laser, or broadband source, okay? Then, number 2, optical source shaping. What do you need? Affinity impulse response filter good making. Number 3, intensity modulation or phase modulation as modulator. Okay, number 4, not required. Number 5, you would require another type of optical filter, FIR, IIR, delay line. And then number 6, you don't need it, etc., etc., etc. So actually, this is something which, of course, needs to be looked case by case, to put the elements, the equations, and to understand why putting this and that element, combining with this and that element, makes that functionality. What I'm trying to show here is that we are trying to be, if you allow me again, generic again. That means we are trying to research on something that can have many uses. Okay? The processor in your cell phone runs many types of applications. Okay? A calendar, a mail, or whatever. And all is done with the same architecture. So, if we want to do all these functionalities, it would be great if we can have a common core. Okay? And that is what we're trying to research. Okay?
If you have a common core, we can simply as we want.
Yes, if you can have a common core, you can reprogram it and do maybe not all, but several of the same several functions with the same chip. Okay? That is it. Up to now, there are only application-specific chips, and we are researching on programmable processors. Okay? So let's put it in a little bit less fancy shape. Okay, this thing here is the same thing on the right-hand side, and I have some examples on the bottom half of the slide to show you how, with this architecture, you can make different functionalities. Okay? For instance, as I said, this is exactly the same, but not in 3D fancy. Okay? The sort, the shaper, modulator, and you can see all the elements there. Again, if you want to do a transmitter, what do you need? This is the same thing than the table, but with fancy properties. Okay? Of course, if you want to do a transmitter, you need the laser or the optical source. You maybe want to filter part of the source to condition it. You need a modulator, and then you need the RF signal to fit it there. This switch, you can put it in, you don't need the output, maybe here, you can pre-filter it, and then the output. Okay? So that would be a transmitter. You don't need this element, you don't need it, you don't need this, and you don't need this because you don't need the detector because it's a transmitter. But if you want a receiver, okay, then it is exactly the same architecture, but using this as input, filter, coupler, detector, RF amplifier, RF filter. Okay? If you want to do an optoelectronic oscillator, actually you end up needing all of them, but without the optical input and output. This is a self-functioning element. This is like a laser cavity, but optoelectronic. Actually, it's like an optoelectronic laser. Okay? So you see your laser here, and with the feedback of your cavity detected, you modulate again the cavity. Okay? Optoelectronic oscillator. And the reconfigurable microwave photonic filters would be this way. In this case, the difference is that in this case, you have only the output for the optoelectronic oscillator, and for the reconfigurable microwave photonic filter, you are actually injecting one external signal. You are not living with the internal signal. Okay, so actually you inject your signal here, modulate. Okay, so basically this switch is not in bar position. This switch is in cross position. Okay. Okay. Any question up to this point? The previous slide? Okay.
How much time do you need to create this circuit?
This?
Circuit?
How much time do you need to create this circuit?
Yeah.
That's a very good question. Okay. That's a good question. You mean to fabricate? Or to design or full cycle? Remember? Both. Okay. Remember before we saw a specification, design, fabrication, and characterization, okay? That in the generic multi-project wafer, where you rely on others' capacity, that can take 8 months, 12 months. Because fabrication is 6-8 months. A specification and design is 2-3 months. And testing is maybe 1 month, 2 months, so 1 year.
At least.
At least.
Testing, packaging, and probably.
Yeah, well, okay. Now, currently, a lot of time. And that is also a roadblock. It should be shorter. Okay. Any other question? Okay, so. Okay, this was microwave photonics in general. I have not discussed about any chip up to this point. Well, I show some filters integrated. Okay.
Did you already make something like that?
That is in the second part of the talk, in 2B. We did actually this one. This one.
It's really hard.
I can tell you later on. I'll tell you now because you asked. We submitted the design in July 2013. If the fab had done the work well in 1 year, we had it, but we published the result last December. So it took like 3 years and a half from design to publication. But only because the foundry was sloppy. I mean, they took 2 years to do something that they can do in half a year. Okay, so 1 year. 1 year. What is hard is to make it work. Okay, in the lab, the design stage in the lab, of course in practice. Okay, we have done this one, and we have done this one as well. Okay, but this one I cannot mention because it's an external cooperation. This one is one of ours, and I'll discuss it at the end of the second part.
Why it's hard? I just like to give a general overview. You need to develop scheme. You need to imagine this scheme that is shown here in slide. Then you need to calculate, to simulate any waveguides, any similar elements in case if you have any kind of technology platform or material, something like that. Then you need to simulate how it will work together, and then you will need to take into account everything including packaging and that's it.
Okay, ideally one would need, as Juliana says, from a systems perspective, assuming some response of this, to calculate the response of the system. Then, for the individual components, to engineer the physics in the circuit to act as if it was in the systems experiment, the system simulation, and then to draw it and to send it to fab and test it. How we did it was, we engineered this, assumed all the rest was going to work well, and fabricated it. And surprisingly, not surprisingly, it worked quite well. Okay? Yes, because this thing didn't exist in the fab, the filter, okay? The laser, the modulator, and the detector, they were there. So we said, okay, let's assume that the specification they are given is quite okay. Let's engineer the core of the problem. And it worked quite well. Of course, it has a lot of things that I'll show you later on, a lot of difficulties, but that can be overcome in time. Please consider that it was done in a generic technology. I mean, the guys in the fab didn't know what we were doing. So they do a circuit for us and for others, and if it works, okay. Okay, it was generic. If we want to do thousands, then we would go and say, okay, change me this waveguide this way because polarization is rotating. I have RF crosstalk there. Please packages, just remove this and make isolation for the RF. So there are a lot of things that we learn there in 3 years, but if we want to make ever a product out of this, I don't think so. We know. Okay. Okay, so motivation for integrated microwave photonics, an application scenario. So basically and I think this is pretty illustrative, this is microwave photonics in the lab and this is how it should look in the market, okay? I won't stay here much longer, okay, because it is needless to say this is bulky, expensive, power consuming, and it has no flexibility, and it takes like a 2 by 1 meter square, okay? But actually, these microwave photonic things should be used in emerging scenarios where the common thing is mobility. And it needs to be, the word in English I think is ubiquitous. It means like it needs to be everywhere. So you cannot be with this everywhere, and you cannot take it in your bag, okay? So you need something that can be in the 5G communication networks, in the antennas, in the base stations, in the central stations, in the smart cities, in these windmills, in the harbor and everything. Even, I think this is pretty imaginative one, wearable technologies with microwave photonics, I don't see it, but in any case people say that it will be there, and the Internet of the Things. So all these are huge number of devices, mobile devices, and everywhere. These cannot be the tabletop in the lab, okay? So that is why we need microwave photonics in an integrated shape. For instance, the case of 5G radio access network. It is predicted that it will have a 1,000-fold gain in capacity, okay? Connecting 100 billion of devices and up to 10 gigabit per second per user. Yeah, that's what I say. I say no. But they say it will, okay? They say it will. So basically, and also it needs to be a global standard, so multi-standard, low latency connections, blah, blah, blah. Those nice things that network people says, okay? In any case, what it is actually true is that there is for instance, if we go to the microwave photonic link example that we were discussing before, there is an interest in reducing the complexity of the cell sites and translating this complexity from the cell site to the core network. Why? Well, if you are going to have thousands, 100,000s of cell sites, you need them to be very simple, because simple means cheap. And that means that you need to shift complexity from the sites to the central office. Okay? That's why here you can see the conventional macro cell site with all these functions in the cell site, and then the central office with a small number of sites, emerging cloud radio access network, which has a little bit more of functions in the base unit, base station unit, and then in the remote antenna unit less functions, and in the future you will have little functions, only the RF optoelectronics conversion and the amplifiers there, and everything that the processing will be done in the core. Do you want to explain that or? Yes, I think the key is there.
Yeah.
Actually, a lot of antennas, simple antennas, complexity to the.
В связи с развитием технологий, таких как, например, интернет вещей, то, что у нас на человека размещают большое количество датчиков, информацию этих датчиков считывают, передают по беспроводной сети куда-то там в офис, медицинский центр. Либо это умный дом, когда вещи управляются с одного мобильного телефона, начиная от холодильника, заканчивая главным мобильником в доме и видеосигналом со всех помещений. Нам необходимо, чтобы на каждой единице, в каждом месте вот этот чип, который передает информацию, стоил как можно дешевле. Что это значит? Чтобы он стоил как можно дешевле, нам необходимо количество функций на нем снижать. Если мы, если мы, и получается, что на данный момент все вот эти фотонно-интегральные схемы, все применения, все подходы очень дорогие, связаны с тем, что большое количество данных, большое количество функций лежит на Это конечная единица, которая весь функционал осуществляет. Если мы перетаскиваем функционал с конечной единицы, которая осуществляет функционал, на какую-то базовую станцию, на центр, и эти все данные обрабатываются, то мы снижаем стоимость конечных элементов и чипов. За счет этого мы имеем возможность глобализации и расширения рынка.
Okay. Okay, so this is how a system looked in the 90s, and this is the equivalent system a few years ago. Actually, this is, maybe you can read the Mel's Griot. It was a supplier of tabletop of pressurized tables, which were 2 by 1 meter square, and this is a wafer, and this is 32 by 16 millimeters square. So actually you have there 16 antenna elements being formed, and there you have 4 antenna elements being formed. Okay. So this has been the evolution. I think that it is quite obvious without going through this thing why integration is helpful. Okay, because it makes you portable and reconfigurable easily. Now, if you think which, because there is also always the question in photonic integration, which is the best technology for this, for microwave photonics? The answer is none is the unique solution. Okay, you have these 3 technologies that I discussed in October: silicon on insulator, indium phosphide, silicon on insulator, and silicon nitride. Each benefits and disadvantages, advantages and disadvantages, and the actual truth is that a combination of 2 will serve in one case or other. A combination of 2, yes. Why? First of all, because the laser you only have it on indium phosphide. Okay, so basically you need indium phosphide. Already need indium phosphide, and then you need either this or this, depending on what you want to do. Okay, in this you have the modulator and you have the photodetector. But for RF photonics, it is a question whether these modulators and photodetectors are quite linear, or they introduce non-linearities. Okay, in silicon. So for some applications where non-linearities are, let's say, not of a concern, you would end up using indium phosphide and silicon photonics. But if you are concerned about linearities, maybe you are willing to use also the modulators and the detectors on indium phosphide and use the silicon nitride, which has very low loss. Okay, very low loss. Where it is? Here, very low loss. And where is it loss? Okay, here. For long propagation delays. Okay. So technologies, takeaway message is a combination of 2 technologies, basically. Indium phosphide and silicon photonics, or indium phosphide and silicon nitride. Okay, so now this is the longest part of the talk, which is the degree of integration and several examples. Okay, so let's try to look for a clock. Okay, okay, let's do that. Are you tired? Okay, let's do that, and then we will make a break, and then consider if we follow or we leave it for tomorrow, whatever. Okay? So now what we're going to see is the degree of integration of different chips that have been demonstrated, and those chips are called application-specific photonic integrated circuits. This PIC preceded by IS. Okay? Application-specific photonic integration circuits. I repeat it again and again because I want to mean it's a chip that can only do one thing. Only one. Okay? So this is a summary of many published examples of different functionalities. Okay? You have functionalities here: filter, arbitrary waveform generation, ADC, tunable true time delay, instantaneous frequency measurement, whatever the functionality. Okay, we don't know about it right now, but we don't mind. If we were to implement this functionality with this generic architecture that serves for all, as I said before, we would require the elements marked in green. Okay, number 1, the optical source, blah 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 blah. Okay, but if you look at the implementation of the different references, for instance, they only implemented, in most of the cases, one filter or the other, or one filter. All the other things, the laser, the modulator, the detector, were external elements. So actually, they had little of integration. In fact, if you just take the ratio between integrated versus the total here, which is actually green squares versus red squares, actually the degree of integration is very low. At most, the 20%, if you look only at photonic components. So up to now, the degree of integration in integrated microwave photonics is or has been very low. Very, very low, okay? So, that is the message here. Let's go through different examples of applications, okay? And now, let's start with reconfigurable delay lines, okay? Reconfigurable delay lines are elements in which you send your signal and you can change the delay they experiment. You can tune how soon they emerge your system or how late they emerge your system, sooner or later, okay? And there are different approaches to do that, okay? One is optical switches, okay? One is optical switches. Basically, it is very simple. It is very simple. You have, imagine these are fibers, okay? Imagine these are fibers with different lengths, L1, L2, L3, and then you have a switch here that you can switch. Okay, that's a switched delay line. That can be done in integrated optics as well. Okay, and then there is another approach which is optical delay line based on optical filters. I'll discuss later on, or in integrated Bragg ratings, which are as well optical filters. This is delay lines, and then there are other things which are important, which are phase shifters. Okay, I'll show you examples of both, and I'll tell you which is good for what and why. Okay, so for instance, phase shift. Okay, I need more blackboard. If I delete with this, I think I cannot write. Okay, I'll leave it there. Here. Okay, try to do it without the blackboard to start. Okay. So this is quite a complex thing. This is a microdisc resonator laser. Okay, a microdisc resonator. This is an indium phosphide chip on top of a silicon on insulator chip. So the microdisc is on indium phosphide, and the waveguide here beneath is on silicon on insulator. If I can draw, basically, is this structure. Okay. This structure. Light goes in, out, partly coupled here, and recirculates. Okay. When I was here in October, we discussed the ring resonators, I remember, and then they have this response. Okay. I'm going to draw the modulus, and I'm going to draw the phase. Okay, response of this element. Okay, light in, light out, part of the light recirculates. So, in modulus, they have this response. Okay? It's periodic. Okay, periodic because there is this periodicity of the round trip time here. Okay? This is wavelength, and this is wavelength. And in phase, they have nonlinear phase. Okay, they are this in this resonance, and the same with the other one. Okay. So, how are these elements used to delay one signal versus other? Okay, and why is this important? I've been talking several times about the beamforming network. You have several signals, which is actually the same signal, copies of the same signal, and you delay differently one respect to the other. That way allows you to do a beam, steer your beam towards the satellite or whatever. Okay, so this can be done with a phase shifter, and this is a phase shifter. And how can be done? Okay, have a look at this graph. This is the phase response, if I'm correct. Yes, this is the phase response. These color lines, forget about the color lines right now. This is your optical carrier, and this is your RF signal, okay, which is single sideband modulated. You don't see the double copy here because it's a single sideband modulation, okay? And then have a look, for instance, at the purple line here, the phase response. So at the optical carrier, you have one phase, and the subcarrier, you have another phase. Okay? So this phase difference is whatever it is, one phase difference, and then imagine that you have an array of these elements, and then you put the same signal, you split it into the array, but to each one you choose a different phase response because you can tune it. So, for instance, in one you use this phase difference, in another one you use the blue, in another one the red, etc., etc. So you have different phases. Okay. So that way, what you are creating is an array of different signals with a different relative delay between the carrier and the optical subcarrier. If you bit them together, imagine the same signal with a different phase, sum and modulus squared, okay, like in a detector. What you get is the bitting, and depending on the phase relations, you can get constructive and destructive. So you could get a filter, okay? If you don't bit them together, but you feed an array of antennas, then you have each antenna element with a phase which act constructively at the detector, which is the satellite, okay? Okay, so basically the phase shifter can help you in beam steering, but it has some difficulties, and I'll tell you later on, okay? There is another way of doing delays, and in this case we are not talking about. Yes. Okay. There is another way of doing delaying signals, which is a Bragg rating. Are you familiar with Bragg ratings? With fiber Bragg ratings, maybe. These are corrugations that you put in a waveguide, for instance. In fibers, it's the refractive index. In integrated optics, it's the dimensions that you change periodically. And in this case, you have this amplitude response because it has a pi phase shift in the middle, so that's why you get these peaks there. And then you have this phase response. Okay. So again, you can put your optical carrier and subcarrier in a given position, and you will get a different relative phase delay between the carrier and the subcarrier. Okay, and this phase delay, depending on the wavelength position here and the frequency, will be one or other. But this graph is pretty illustrative. Okay, have a look at the frequency. Okay, have a look at the frequency and the phase. Okay, in this case, what you get is a linear dependence of the phase versus the frequency. Keep that in mind, okay? Keep that in mind. Keep that in mind because there is another way of doing. I think I'm going to skip. Allow me to skip forward a bit, and I'll come back later. Okay. Okay. I'm going to show you this example, and then I'll come back to the technology that has created this example. I think it is better to see it from top down than bottom up. Okay? My feeling. I'll confirm it later with you. So, now, imagine that you have this scenario which triggers some smiles around the satellite and moving target, pointing, etc. Okay? Usually, you are not transmitting an RF carrier. You have a modulated signal, which is multiple frequencies around the carrier. Okay? So, you need to ensure that all the frequencies are pointing in the same direction. To do that, you need to do what is called true time delay. True time delay means that all the frequencies get the same delay. Okay? True time delay means that all the frequencies get the same delay. This is illustrated here, and this compares a phase shifter with a true time delay network. Okay? Let's have a closer look to these graphs here. In this graph here we have pointing angle, the pointing angle, versus frequency. Okay? Ideally, one would have to be this. That is, pointing angle versus frequency, flat line. All frequencies pointing more or less in the same angle, 29.9, 30.2, more or less in the same angle. Here you have this frequency, 10.7 gigahertz, pointing towards 33.15, and the other one, on the other side of the band, pointing to 27.3. Okay? If you look at the beam that is shining in the antenna, that corresponds to this position pointing toward that position, and this corresponds pointing toward that position, and this in the middle, which is the ideal, is this one here. Ideally, you would have all the frequencies the same beam, pointing in the same direction. If you use a phase shifter, you cannot get that for a broadband signal, okay? Because a phase shifter does not preserve the linearity in phase for all the frequencies. That, without seeing the equation, it is, let's say, you need to believe it, okay? Sorry for that. When I was attending the conferences, I didn't like that, but okay, we don't have all the time in the world, okay? So I've been presenting phase shifters, but there are ways of doing true time delay with phase shifters. And basically the key is you need to preserve a linear relation between the subcarrier and the optical carrier, okay? Here is your sideband. You need a linear relation in phase in the subcarrier, okay? You can do that with a phase shifter, but then the phase shifter phase is that way. You don't have a linear relation. This would be the ideal linear relation preserved for the carrier and the subcarrier. If you do it only with a phase shifter, only with a ring resonator, with one single ring resonator, you cannot attain this linear phase shift and the true time delay. So basically what people does is to employ different ring resonators cascaded to each other. Okay? One is to make linear the phase here, and the other one is to compensate for the non-linearity of the previous one. One processes the subcarrier, the optical delay unit, and the other one processes the optical carrier. Okay? And this is done in a microchip with silicon nitride waveguides, the size I mentioned before, 16 antenna elements in a chip which is, I believe it was 32 by 16 millimeters. Okay. This is the layout of the chip. This is how it looks at the side of a 20-cent euro coin. And this is the application and the results. Okay? Questions up to this point? So this is one very specific chip of application as a beamformer. Okay, so let's go ahead then. Arbitrary waveforms, as I mentioned, these are techniques to create signals which have many shapes. Okay, the shapes that are required by a given regulation. For instance, there is a regulation by the US FCC that gives you a template on how to fill the spectrum. Okay, for instance, these frequencies with this power, these frequencies with this power, these frequencies with other power. How to do that? Well, there are techniques, for instance, one I'm going to show now, which is space-to-time mapping. Okay, space-to-time mapping. And this is the technique shown in this chip. This chip was done by several ring resonators. Okay, a ring resonator which is tunable. And in this case, what you are injecting in the ring resonators is a train of pulses. Okay. And the ring resonators and the time repetition and the width of the pulses is compatible with the round trip time of the ring resonator in such a way that this is what you get in wavelength, and when you make it go through a fiber spool and make back a conversion to RF with a photodetector, you get these pulses. Okay, you get these pulses. So actually you enter with one pulse, you shoot it into an array of ring resonators. Each one gives back one pulse, so you end back with a train of pulses. Okay, with a train of pulses. Each one at a different time because you enter different wavelengths here, the different wavelengths, and then you have dispersion. So actually you separate them in time. Okay. If you look at the spectrum, the RF spectrum has this shape. Okay. Usually on these ones, one superimpose this template that I mentioned before the regulation. Okay, so this is arbitrary waveform generation using ring resonators. Okay, there are other ways of doing this. This one is using phase modulation, for instance. Okay, so if you have an optical signal, okay, and you have a phase modulator you can imagine that the optical carrier moves in frequency to towards one end or towards the other. Okay? If you put that on the edge of a ring resonator, the ring resonator is still, you don't modulate it, you modulate the phase of the laser. Basically your laser is doing this or this. Okay, so it's getting higher amplitude, lower amplitude, higher amplitude, lower amplitude. Okay, so you can do this in a positive or negative slope way, and you can combine them, and then you get a doublet. Okay, basically you get a combination of this, and if you do that in a pulse manner, I mean if the laser is pulsed, you get pulses with a different shape. Okay, and that, if you turn it back into the RF spectrum, again is an ultra-wideband generation signal with ultra-wideband generation. Okay, questions up to this point? Okay, and then we've seen filtering and delay, we've seen generation, and now we're having a look at transmission systems. Transmission systems, we've seen in the introduction that the microwave photonics link have a figure of merit, which is the dynamic range. Basically, how far are we from the top of my carrier to the noise and the intermodulation problems. How can one increase the distance? Okay, obvious answer. More linear elements that are more linear. Okay, increasing power sometimes. Okay, but one of the modulation schemes which is intrinsically linear is the phase modulation. Okay, the phase modulation. You can modulate in phase as far as you can get with your voltage without breaking your modulator. You get all the dynamic range there. Okay, compared to a Mach cylinder where you have your V pi and you have your nonlinear curve, well, it is more nonlinear. But that would be nice, replacing the intensity modulator by a phase modulator, which, by the way, you are familiar with phase modulator. But then that means that you are modulating in phase, not in intensity. And if you want to detect that modulation, you can do two things. One is a frequency discrimination, okay, and a balance detection. And the other one is a coherent receiver. Okay, so to detect a phase modulation, you have two alternatives. I will try to explain it with my hands, just making like this. If not, I'll draw it. Okay, it's already right. Okay, so basically, if you modulate in phase, I was saying that your optical carrier is doing this and this, this and this, right? From the central position to the sides. A frequency discriminator is a filter that tells you when you are on this side or when you are on this side. Okay, so a frequency discriminator, you feed the signal, and yes, the upper branch and the lower branch tell you signal is on this side, signal is on this side. Okay, and if you make a balance detection of it, which means signal is on this side positive, signal is on this side negative, if this is a sinusoid, okay, going up and down. If you make it one part negative, then you get again the sinusoid. Got it or not? Did you get it? I'm not sure. Okay. Yes. It's sort of rectifier, but with negative amplitude. It's like you are modulating your phase modulator with a sinusoid. Okay. And that means that your spectrum, if you look at the spectrum, your spectrum is shifting this way and this way, positive and negative cycle. But in amplitude, the photodetector is square. Okay. So you need a balanced detection, one which is plus and one that is minus, to be able to recover the sinusoid. If not, you will get this. You will get two positive things. Okay. So that is one thing, the discriminator. And the other thing is a coherent detector. A coherent detector is, okay, I want to recover my phase modulation, I have my laser, my phase modulation, and then I need to resort to another laser and another phase modulator. I beat them coherently. This is an optical coupler, it should be an optical coupler. I give a balance detector, low pass filter, and then try to lock myself. This is like locking myself to this phase modulation. This is complex, but it is very good. This is cheaper and this is less good, let's say, in terms of the figures of merit. Okay? Most of the research that we've seen in photonic integrated circuits, in application-specific photonic integrated circuits, has been on the first type. Okay, on the first type. So basically, again, it reduces to design a filter that splits the upper band, the lower band, and the upper band. Okay? And that is what these guys did with their ring resonators again. So basically, it's something that splits the band and it provides a linear slope in wavelength. Okay? So actually, when you split the bands and you have a linear slope, you get linear slope on this side, linear slope on this side, and then this one in a negative balance photodetection, then you get your discriminator. Okay? This one was done in silicon nitride, and this one was done in silicon on PLC, sorry, PLC, silicon. Okay. Questions up to this point? Later on, in the second part, I'll describe one of our discriminators. Shall I continue? Yeah. Will I continue? Let me have a look. I don't remember how much I have before ending the first part. Yes, it is like we are 7 slides away. Break. For me, it would be good break. Yes. Okay. So now I have introduced discriminators. Please, if you didn't understand very much, don't worry, because in the second part I will stop more on discriminators. Okay. Then I'm going to talk about filters, which is one of our applications. Okay, as well. So to do filters in photonic, in microwave photonics, you can resort to 2 regimes: the coherent regime and the incoherent regime. Okay. What is the coherent regime? Coherent regime is I want to do an RF filter with a given functionality. Then I use photonic techniques in such a way that the same shape that my photonic filter has, it is translated into RF. Okay, so actually, it sometimes is called frequency mapping, because you get your photonic filter in wavelength or in optical frequency and you map it directly into the RF. How is this done? Okay, in that case, what you need to do is to modulate your signal again in single sideband. You've been realizing that single sideband is quite important in all these techniques. Okay, single sideband, and then you put it through your optical filter. Here you have superimposed the optical filter. Okay, and you can see the optical carrier and the subcarrier. When you filter this with this filter and you beat it, it is exactly the same as having the filter for the single RF signal. Okay? Basically, is, as I said, translating the optical filter to the electrical domain. Okay? There have been many demonstrations of this. These are rings and Mach cylinders embedded into rings, where, as I said, you can activate the poles and the zeros. You can put them in very arbitrary shapes, and basically you can very arbitrary positions and get arbitrary shapes of the filters. This has been done in indium phosphide. Again, one single application for the device. It has been done with ring resonators as well. I'll link the slides just in case you are specifically interested in one of the cases. There are references everywhere. And then there is the incoherent regime. In the incoherent regime, you actually end up having multiple copies of the signal, which are somehow delayed a different amount, and then they beat together. Okay, this I already mentioned. And with the beating, you control different things. For instance, the number of signals delayed gives you the order of the filter. Okay. The number gives you the type of the filter and the quality, the fineness of the equivalent RF filter. Okay, this is the phase if the delay between samples, this T to T, gives you the spectral period, okay? It's a spectral period. If you change the delay, you change the spectral period. And the amplitude coefficients, if you are able also to change the relative amplitudes, gives you the filter shape, which basically the filter shapes give you the side lobe level, either this side lobe is closer or lower. And the phase coefficients in this summation, which you cannot see there, but in the slides it's pretty well shown. What you change is the position of this thing, the tubing. Okay, so you have many degrees of freedom in the incoherent regime. But one of these advantages, first of all, that you need to make multiple copies of your signal. And second of all, the delay which is used here is usually as a draw in the blackboard. Multiple lanes with different lengths, okay? Or you can do it using different wavelengths in a dispersive delay line, okay? Instead of parallelizing one wavelength in the spatial domain, you can do multiple wavelengths in the wavelength domain, and each one will see a different propagation delay. That up to now has been done using optical fibers, which are okay, but as I said, these are not integrated components. And some years ago, some people in our group made it with a photonic crystal waveguide. Okay, a photonic crystal waveguide which has a nice dispersion profile in the edge. Of course, it has losses, but it acted as an optical fiber, and we were able to get, or they were able to get, equivalent microwave photonic filters in the incoherent region. Okay. And this one, the instantaneous frequency measurement, I'm going to leave it for the other part where I will explain it better. Okay. So to summarize this first part, again the same slide. The message is that you've seen many chips of application in the different domains of microwave photonics: transport, signal generation, delay, and the other one I don't remember right now. And you've seen that the degree of integration is very low. Okay? So the push in this field is to integrate further and to make it multifunctional. And I'll show you some example of integrate further. To make it multifunctional is a project that, one of the projects that we are also studying. Okay. Questions? Great. Yes. Yes.